In this video, we're going to start chapter 6 of the calculus textbook. So this is the second chapter in Calculus 2, Integral Calculus. Chapter 6 is on applications of integration. And in this video, we're going to go through section 6.1, which is using integration to find areas between curves. Okay, and so as I mentioned in the previous video, when we go through these applications of integration sections, yes, we want to see what the actual application they're illustrating is, so we could potentially use integration for that application. But we also want to focus on how is integration or the infinite sum tool, how is it being set up to solve these problems? So, imagine we were given this problem of how do you find the area between curves, and we had to derive this integral ourselves from scratch. How would we do it? You want to think about that, because one of the skills that we're trying to get when we're done with calculus is if we have a problem that we're trying to solve, that problem might be able to be solved using integration. And so you need to be able to see, okay, well, how can I break this up into pieces and then take the limit as those pieces go to infinity, and then so write that problem as an integral. So, okay, areas between curves. In Chapter 5, we defined and calculated areas of regions that lie under the graphs of functions. Here we use integrals to find areas of regions that lie between the graphs of two functions. So like shown here, okay? And when we developed integration, we just strictly looked at the area under the curve, or between the x-axis and the curve. The area, that's what we call the area under the curve. So you can see here we're looking at the idea of what is the area between two curves. So consider the region S that lies between two curves, y is equal to f of x and y is equal to g of x, and between the vertical lines x is equal to a and x is equal to b, where f and g are continuous functions, and f of x is always greater than or equal to g of x, at least for within the interval from a to b. Okay, so we're trying to find the area between this curve and between the vertical lines at x is equal to a and x is equal to b. And a constraint here is that the f of x is always greater than g of x, at least within the interval between a and b. It changes here, but within the interval we're evaluating, that's the case. All right. Just as we did for areas under curves in section 5.1, we divide S into n strips of equal width. Okay, so that's always going to be the process. When you're trying to integrate something, you're going to be dividing you're going to try and look at the problem and say, okay, what am I trying to solve for? All right, so let's try and break down how they're doing this analysis. The first thing, I guess, when you have a problem to solve, the first thing you're going to do is, and I want to stress that we're going to see problems that with integration that aren't about finding areas. So it's not always about areas. Like might want to find the length of a curve, so it's not always about areas. Okay, but the idea is, though, you have a problem that you're trying to solve for, and you want to try and, I guess, if you can, pictorially or graphically represent what you're trying to solve for. So here, they draw what they're trying to solve for. Okay, it's this area of this region S. So you have a visual idea, or at least a descriptive idea of what you're trying to solve for. Then you think about, okay, can I take what I'm trying to solve for and break it up into pieces? And then think about the idea of summing up those pieces to get, if I'm not taking the limit as those pieces go to infinity, if it's like a finite number of pieces, when I sum those pieces up, I get an approximation for what I'm trying to solve for. If you can, if the problem you're trying to solve, you can think about it that way, then that's going to be applicable to integration. All right, so we approximate, so we can do that. We can break up S. We can think about breaking up S, the area we're trying to solve for, into n strips of equal width. Okay, and that's going to be another thing too. Based on integration, it doesn't technically have to be the case. This doesn't have to be the case, but the way we talked about it, for most cases, if you're using the infinite sum tool, you're going to be breaking up what you're trying to solve for into pieces that have like a equal width with respect to the independent variable. It's only going to be the dependent variable where it's going to make them not the same size, the pieces. Okay, so they have equal width, and then we approximate the ith strip. So like, we have strips from I is equal to 1 to n. So the ith strip by a rectangle with base delta x and height. Okay, so in this case, you're going to have the rectangle is going to have width delta x. All the pieces are going to have the same width delta x, and then each piece's height, it's calling it in this case, is going to be f of x star minus g of x I star. F of x I star minus g of x I star. And what they're saying is, so you have a bunch of pieces of equal width going from A to B, and then the height of those pieces is going to be f of x minus g of x. And that makes sense because then you're adding them up because g of x is going to be negative, at least in this region. But here g of x is positive, but so it still makes sense because f of x minus g of x is this height. Whereas here, f of x minus g of x turns into f of x plus g of x because g of x is negative. So you get the correct height, okay? And so, I'm trying to get away. We're thinking about rectangles still, but I want to try and push to where we can get our minds thinking in general, not just about rectangles. So again, the width, okay? The width, these we're going to be breaking up what we're trying to solve for into n pieces. They say strips. Here it is strips, but in general, it's going to be in pieces of equal width. And what they mean by that, it's going to be the size of these pieces in general is going to be the size, we're going to be breaking it up with respect to the independent variable. Okay, so we're going to see problems later in this section where y is the independent variable. So we find the area under the curve between the curve and the y-axis. So in that case, you're breaking it up along the y-axis, the pieces. It's the independent variable is what you're breaking up into equal widths. That's the width. Okay, and then each of those equal widths, you're going to be multiplying by some value that's associated with the function. Either one or multiple functions. It's going to be the dependent part, the part that's a function of the independent variable. That's what's going to dictate you can think about the height of each of those pieces that you've broken up the quantity you're trying to solve for into. And so in this case, let's just look at this specific problem. We can see how, all right, well, we're breaking this up into strips. Definitely we're breaking up into strips. And each of those strips is going to have an equal width with respect to the independent variable. And then we can see what the height's going to be. We would take, so this xi star here means we can evaluate the function at any position within that strip. The left endpoint, the right endpoint, the middle, whatever. And you just take that x value within the strip, evaluate the function at that x value, the f of x, and subtract that from the function that g of x evaluated that value, and that's going to be the height of each strip. That's going to be, when I say height, you're going to multiply delta x times that value. Okay, and so with that, we can write the Riemann sum. You have the delta x, which we can see the delta x is going to be b minus a divided by n in this case, and then it's going to be f of xi star minus g of xi star. So there's the Riemann sum, right? And so they give a sense of the Riemann sum here. Here's a typical rectangle. Here's f of xi star minus g of xi star. This is f of xi. This is g of xi. There's the delta x. And so here's, if you do 1, 2, 3, 4, 5, 6, 7, 8, 9 rectangles, this is the approximation. But it says the approximation appears to become better and better as n approaches infinity. And so that's, I think, when you're trying to set up an integral on your own from scratch, if you want to do what they're doing here, so they first drew a graph or a picture, either an actual picture or maybe just write out a description if you can't draw a picture. Then they make it seem apparent that, okay, you visualize what your quantity you're trying to solve for is, and you think, okay, well, this could be solved for if I break this up into pieces. Okay, the pieces are going to have equal width with respect to the independent variable, and then the heights of the pieces are going to be based on the problem. Okay, so you write out, so you get an idea of what you want to do. You write out your Riemann sum. So you'll have the delta x or the delta independent variable, and then you'll have some function that represents the height. Okay, and then the next thing you can do is, draw a picture or write out a description that shows one of those pieces, and then draw another picture that shows like an approximation using 6 or 7 of those pieces. and then say to yourself, okay, as n goes to infinity, as the number of pieces go to infinity, is it apparent that, yeah, gets better and better and better and better, right? Because it might be the case that you think that you could break up the quantity you're trying to solve for into pieces to solve the problem, and then when you draw it out and actually think about those pieces, the number of those pieces going to infinity, it actually is very clear that it's not becoming a better and better approximation for the value you're trying to solve for. So then you would have to, start over. Like what they're doing here is, so we talked through what should the Riemann sum be. Okay, we talked through it, and this is what we got. This here is verifying, is this the correct Riemann sum? Let's draw one of the n pieces, and then let's draw an approximation using like 8 pieces. And then think about, okay, so as the number of those pieces go to infinity, is that it seems very clear that that's approaching the value we're looking for. And that's the case. They say yes, it is. Okay, so therefore we define the area A of the region S as the limiting value of the sum of the areas of these approximating rectangles. As n approaches infinity of the Riemann sum, that's the area we're looking for. That's the area between the curves. Okay, so there we go. There's the area. Next step is, okay, but we want to write this in integral notation. How do you do that? Well, this is the elongated S symbol, the sum from I is equal to 1 to n, the infinite sum. That's the elongated S symbol. There we go. You put your limits of integration, because with the infinite sum tool, it's for any infinite sum problem, there's always an upper and lower limit. So you put the B and A, then you just put the function. You don't, because as n goes to infinity, this xi, the actual x position within each interval makes no difference. You just put the function. Now with the fundamental theorem, there is no summing anyway, because we use the fundamental theorem to solve this. So there is no summing anyway. But that's how you can think about it. You might be wondering, okay, well, when I'm putting this in integral notation, do I think about left endpoint, right endpoint? When it comes to integrals, there is no left, right, endpoint, midpoint. You just put the function. Okay? And then as n goes to infinity, delta x gets infinitesimally small. So you put dx. And there you go. There's the formula for the area between two curves. Now, this isn't completely general, because it says the area A of the region bounded by these two curves and the lines x equal to A, x equal to B, where f and g are continuous, but then f of x is always greater than or equal to g of x for all x in A to B. So it's this case though. We haven't talked about the case where maybe f of x is not always greater than g of x. Okay, so f and g are continuous, and if they aren't continuous, then you'll have to like break it up in between the discount. You have to do this between each the discontinuities, but it's saying in general though, f and g are continuous, and f of x is always greater than or equal to g of x within the interval from A to B. Okay, it says, notice that in the special case where g of x is equal to 0, S is the region under the graph of f, and our general definition of area 1 reduces to our previous definition. Yeah, if g of x is equal to 0, then it's just the area under the curve of f of x, like it's the original integral definition. Okay, in the case where both f and g are positive, you can see from figure 3 why the equation 2 is true. Yeah, if f and g are positive, there's no problem. We talked about it. G doesn't have to be always positive. Neither does f. You could have f be negative and g be negative. It still works fine. It's any case. It makes no difference what, if f is positive, g is positive, whatever, as long as f is always greater than or equal to g throughout the entire interval, then that formula works. Okay, so they do a couple of examples here. Just some standard examples, and we'll work a bunch of example problems like this in the next video. But it says here, okay, let's take a look at this. Sometimes it's difficult or even impossible to find the points of intersection of two curves exactly. As shown in the following example, we can use a graphing calculator or computer to find approximate values for the intersection points and then proceed as before. So what they're saying is you want to find the area of the region bounded by the curves, these two curves here. And so they draw the two curves, and what we're looking for is this region here, the area of this region. And we can use that equation too, because we have a curve that this curve is always greater than or equal to this curve within the 2 points. But what are those 2 points though? Like, what's A and B here? Well, it's these points of intersection. And so you find the points of intersection by setting the functions equal to each other and solving for x. And this happens to turn out to be an equation that it says it's impossible actually to solve this. All right, but what they talk about is that you can use like a graphing software like Desmos or whatever, or your calculator, to get an approximation for these points of intersection. But then also you can use like numerical methods. This is the kind of thing we're going to talk about in numerical methods. It's like Newton's method, where we didn't go into Newton's method explicitly, but this would be a perfect scenario for a numerical method that you can use to solve this, and you could get these points of intersection to whatever amount of accuracy you want. Here, there's just 2 decimal places, but you could do 5 decimal places, whatever. You just can't get a literal exact answer as far as like mathematically exact, right? If you're a mathematician, a PhD major, and you're trying to solve math theorems, then in general, you're trying to get exact solutions. But this course is more for people that are applying math, like engineers, scientists, business people, chemists. And so numerical methods is great if you're just trying to apply the math for real situations. And so that's what they're saying. They use the graphing software, the graphing calculator, to get this is the origin, and this is x is equal to about 1.18, and so that's the limits of integration. You just subtract the 2 functions to get the area but between these 2 points, A and B, and that's the area of the region, the area of the region bound by the 2 curves. Okay, here it says this figure shows velocity curves for 2 cars, A and B, that start side by side and move along the same road. What does the area between the curves represent? Use the midpoint rule to estimate it. So that they're saying do this numerically. So you set up the Riemann sum using the midpoint rule, the Riemann sum, but for the area between the 2 curves. And they're just asking, okay, what does the area between the 2 curves represent? This is the velocity for 2 cars A and B that start side by side and move along the same road. And so the area between the 2 curves is the distance. We're estimating the distance between the 2 cars. It's an estimate because we're just using the midpoint rule. The distance between the 2 cars after 16 seconds. So it's the area under curve A from between A and the horizontal axis. That's the distance the car A traveled in 16 seconds. And then we're subtracting from that the area under curve B, the distance car B traveled in 16 seconds. And so we're left with the area between the 2 curves. That's the distance between the 2 cars after 16 seconds. Okay, and the solution shows they break this up into 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces. And then so they assume the velocity is constant within each of those pieces, but the height, but the velocity is equal to the function evaluated at the midpoint. So yeah, it's just the midpoint rule. They use the midpoint rule, the midpoint Riemann sum with 9 pieces to estimate the area between curves A and B. Okay, so here it says figure 9 is an example of a pathogenesis curve for a measles infection. It shows how the disease develops in an individual with no immunity after the measles virus spreads to the bloodstream from the respiratory tract. All right, so the dependent variable is the number of infected cells per milliliter of blood plasma, and here's the days since the infection started. The patient becomes infectious to others once the concentration of infected cells becomes great enough, and he or she remains infectious until the immune system manages to prevent further transmission. However, symptoms don't develop until the amount of infection reaches a particular threshold. The amount of infection needed to develop symptoms depends on both the concentration of infected cells and time, and corresponds to the area under the pathogenesis curve until symptoms appear. Okay, so the amount of infection needed to develop symptoms depends on both the concentration of infected cells and time, and corresponds to the area under the pathogenesis curve until symptoms appear. Okay, so the pathogenesis curve in figure 9 has been modeled by, here's the function for that curve. This is the number of infected cells as a function of time. if infectiousness begins on day T1 is equal to 10 and ends on day T2 is equal to 18, what are the corresponding levels of infected cells? So that's just F of 10 and F of 18, right? Yep. F of 10 is 1,210 cells per milliliter. F of 18 is 1,026 cells per milliliter. Okay? The level of infectiousness for an infected person is the area between N is equal to Ft and the line through the points P1 and P2 measured in cells per milliliter times days. So the level of infectiousness for an infected person is the area between, oh, I see, okay, yeah, where the P1 and P2 are the days when infectiousness begins and ends, okay? So P1 is F of 10, P2 is F of 18, and the level of infectiousness is the area between, is this area between this line and this curve here. And so what this is going to be is you're going to have, this is going to be like G of T. This is going to be F of T. And the domain is from 10 to 18, from T is equal to 10 to 18, because both of these are a function of T. And you're just going to take the integral F of T minus G of T dt from 10 to 18. Okay? That's what they do. And we're going to work examples. We're going to work examples just of general finding areas between curves, as well as application, word problem examples as well, like this. All right. It says here, what about the situation where you want to find the area bound between two curves, but one curve isn't necessarily always greater than the other curve over the interval? So it says, if we are asked to find the area between the curves y is equal to f of x and y is equal to g of x, where f of x is greater than or equal to g of x for some values of x, but vice versa for other values of x, then we split the given region S into several regions. Okay, so like here's region 1, here's region 2, here's region 3. So we want to find, in this situation, 3 separate areas. We then define the area of the region S to be the sum of the areas of the smaller regions. Okay, so they're saying that the total area is the sum of the smaller areas, S1 plus S2 plus S3. And if you think about it, what you can do is you can split this into separate integrals. So, and add those integrals. So you would do the integral from A to here, and then you would do f of x minus g of x, and then the integral from here to here, g of x minus f of x. And so you'd have these 3 separate integrals you'd add up. And it points out that if you think about the absolute value of f of x minus g of x, and so you could write that as a piecewise function. It's f of x minus g of x when f of x is greater than or equal to g of x, and g of x minus f of x when g of x is greater than or equal to f of x. Right? So the idea is to find the area between two curves, like we've talked about in this section. You always want to subtract the greater function from the lower function, the higher function from the lower function. And so if you think about the absolute value of the difference between two functions, that's what this is doing. So you could actually write equation 2, the equation we developed first, you could actually write it this way, that this is valid, this includes equation 2. Because if f of x is always greater than or equal to g of x for all a to b, then you just remove the absolute values. If it's not, then you're just going to have to break up the integral into separate integrals. Because that's what the absolute value means. Right? It's like you have to break it up. This you'd break up into, so here you'd break this up into 3 separate integrals. Okay? And then it gives an example here, and one thing to look out for is potential symmetry. So if you're trying to find the areas between these two curves, you would use this absolute value method here. So you'd have 2 separate integrals, but if you think about the symmetry, then you could actually just do one of the integrals and multiply by 2. All right, here it gives an example where to solve this, it's easier to treat y as the dependent variable. So I guess, I mean, I'd have to look at this, but you could technically treat, well, no, you couldn't treat x as the independent variable. I'd have to look at it, but, or maybe you could treat x as the independent variable, but then, I don't know, I'd have to look at it, but it's definitely easier in this scenario to treat y as the independent variable. And you split it up into rectangles like this. And so that way, you always have, it's always like this function minus this function throughout the entire range. But if you did it along the x-axis, it would be, you'd have one portion would be just involving this first function. Then you have another function that would be involving the two functions, you see. You could still do it, but you have to break it up into like two separate problems. Okay, but in the next video or the upcoming videos, we're going to work every type of example problem that they show here in the section. So we'll get plenty of practice with all of this. All right, let's work some example problems.